Good afternoon, everybody. My name is Charlie Nicklin, I'm Chief Executive of IAgrE, and I'd like to thank you all for joining our September presentation. I'd like to welcome back IAgrE member Paul Mwebaze from the University of Illinois for today's lecture. Paul is an agricultural economist and project manager of SCAPES, which is based in the Institute of Sustainability, Energy and Environment at the university. Just over 2 years ago, Paul presented to us on a US Ag Department funded project on the economies of using land for both food and energy production. Today's lecture will update us on the opportunities and challenges with the project so far. As usual, everybody will be muted, and if you want to ask questions, please pop them in the chat at the bottom of the screen, and then at the end of the presentation we can unmute you so you can ask in person. Okay, I'll now hand over to Paul.
All right. Thank you so much for the kind introduction. It's good to be back here. Last time I presented some of the research we were doing on the SCAPES project. Let me try and share my screen. So last time I spoke about the co-location opportunities through this project called SCAPES, Sustainable Co-locating Agriculture PV Electricity Systems. We've had 4 years. We're at the end of this very big project. This was a $10 million grant. And so today I'm going to present some updated results. We are a very big team. We have economists here. We have engineers, mechanical and agricultural engineers. We have agronomists and we have social scientists. And so today I will be presenting some updated results from this work. And so the topic for today is sparing cropland for solar energy or sharing through agrivoltaics. And I will dive into the details, what we mean by that. And so what we've been doing in this project is looking at deploying agrivoltaics on large scale. There's lots of experimental studies that have looked at this, but they're small size, few acres, 5 acres, 10 acres here, and you cannot draw firm conclusions based on small scale. So this project was looking at large scale deployment of solar and agrivoltaics on row crops in the US Midwest. Just as a motivation, just to explain why we care so much about this. So there's been rapid solar expansion into cropland, which is causing conflict. And so utility scale solar has been rapidly expanding, especially in the Midwest. And there's some statistics I put up here. 67% of solar as of 2020 is happening in the Midwest. And the reason for that is because of the flat land. It turns out that solar panels and crops share the same requirements for productivity. So the flat land, being close to electricity grid, being close to population centers, has driven the demand for solar energy. At the aggregate scale, at the big scale, like at the country level scale, the land requirements is actually modest. And I'll show some numbers later in the presentations that just a small fraction of the land is actually required to meet solar energy targets for the entire US. Problem is that the impacts are highly concentrated. They're very high in some locations and almost zero in others. And that's what is causing local resistance and sort of community opposition to solar. And so community opposition comes from concerns about food production impacts, because you're taking land, productive land away from food production and using it for energy. It could have positive or negative impacts on land values. Some neighbors have been concerned about impacts of solar on their land values. And then there's aesthetics. Some people just don't like the look of industrial scale solar panels behind their houses or in near them. They would rather see beautiful green cornfields, as they said. And then there's also equity issues. Solar energy can create both winners and losers, and I'll explain that a little bit later. And so this raises this question: how should we allocate land for food and renewable energy production? There's two approaches here: this sparing cropland and then sharing it through agrivoltaics. And I will explain what these are. And so these two competing approaches, sparing versus sharing. land sparing approach, we use the land. We use the most productive land for food crops. And then we use the less productive cropland, like marginal land with low productivity that is then used for solar energy to minimize impacts on crop production. So that's land sparing. And then land sharing is co-locating crops and solar panels on the same land. And you do this through AgriVoltaics. There are trade-offs with both of these approaches. So for example, for land sparing may be efficient for food production because you are using the most fertile, prime cropland to produce crops. But then that's going to be less productive. That means that less productive cropland may not be the most suitable for solar energy generation. On the other hand, agrivoltaics has got promise, but is largely untested. Agrivoltaics has been experimented with specialty crops that are short and do not have tall heights. In fact, in the US, only 8% of US agrivoltaic sites, they do plant crops, and most of these are specialty crops. So agrivoltaics has not really been tested with row crops, corn and soybeans. And as you probably know, a lot of land in the US Midwest is covered with corn and soy production, millions of hectares of land. And so it's important to examine this question, how compatible agrivoltaics could be with row crop production. So this picture below is this is a stylized depiction of an engineering design of what agrivoltaics with row crops may look like. And so you can see here, we have solar panels. They're lifted almost 8 feet above the ground in order to allow equipment to pass through. So we have here a conventional tractor, and that also needs space in order to be able to navigate through. And so you can see the spacing between the panels is a little bit wider. And so you need to make all of these adjustments. And then you need, for example, you need boundary buffer here. Tractor needs to turn at the end without damaging the panels. You need to leave a bit of land between the panels and the crops in order to reduce potential damage to equipment. So this is the kind of layout that the SCAPES project has been working on. This is what we've come up with, some of these dimensions. It means the spacing between the panels is going to be wider. The panels are going to be taller in order to allow conventional equipment to pass through. So the research questions, and this is a working paper. So the research questions that we pose in this paper are the couple of questions here. So how do land sharing versus land sparing approach for food and energy production compare for meeting projected solar energy targets for the US for 2050? And we focus on the eastern part of the US because that's the rain-fed region with a lot of corn and soybean production. So how do those two approaches compare? What are the impacts on the amount of solar generation possible on cropland? What are the costs of energy generation and the impacts on crop production? And even more important is amount of land that is required to meet the same food crop production level. And so underneath all this analysis is the need to understand profitability of agrivoltaics versus PV alone, agrivoltaics versus crop production alone. Because as a solar developer has got two choices. They can do, and I addressed this in the last presentation, they can choose to do solar only because maybe that could return higher profits to them. Or they could choose to do agrivoltaics. And so one of the metrics that they're going to use to decide is going to be profitability. And then we also need to look at the impact of agrivoltaics on crop yields. What do they do to crop yields? We've been doing this kind of work for past few years. And I will be sharing some results here. So to get into the details, so this is what agrivoltaics with row crops looks like. The slide, so the picture on the right here, the first picture here is compares PV layout. Let me see if I can get a pointer. Okay. There's a pointer here. All right, I'll use that. So this is a PV layout setup. This is intended to maximize electricity production. And you can tell the spacing between the panels here is just 18 feet apart. And there's a higher density of solar panels, okay? And then on the other side here is what we call an integrated agrivoltaic system. And here you have rows of crops. This is the green thing, this green part, these are rows of crops that is interspersed between the panels. And as I mentioned, to do that, you need to have wider spacing. You can see, I'm not sure you can see this figure, it's 43.5 feet apart to allow for that. And so to achieve agrivoltaics with row crops means raising panel height at least above 4 feet. So you're going to 6 to 8 feet. It's going to cost you more in terms of engineering costs. So the capital costs are going to be higher, 2 to 3 times more to install compared to a standard utility, increasing spacing, and then keeping unused land as a buffer between crops and solar panels to prevent damage. So this is the configuration that I presented last time. Here is our conventional tractor. We're assuming that you need this space for this tractor to operate smoothly. And so what's interesting is we can start to compare energy generation and crop production under these two alternative approaches. So this, let's look at energy generation, for example. So under an integrated agrivoltaic system, and these units are in kilowatt hours per kilowatt. So this is a measure of productivity of energy. And so immediately you see here that actually energy generation is going up. So you have a slight increase kilowatt hours per kilowatt from an integrated system. And I can explain this a little bit later, but basically this is coming from vegetation underneath the solar panels that is helping to cool the solar panels. So there's some cooling effect happening here that's contributing to a small boost. There's a small increase in energy generation. And this is PV only. It doesn't have this vegetation. So this cooling effect is sort of one beneficial aspect of agrivoltaics. On the other side here is bushels. Sorry for the units. These American units. So these are bushels, acre. And you can see that when you produce only crop only, so this is soybean only, you're getting about 67 bushels per acre. And under an integrated system, because of the spacing, because of the shading impacts, you're actually getting a yield penalty. So you're getting 55 bushels per acre. And so these are the dynamics that are in the background to consider. And so developers, all they care about is profitability. So here in this slide, in this first part that I'm highlighting here, I'm showing the annualized costs and returns of PV and agrivoltaics from the perspective of solar developers. So this is what solar developers are looking at. So from doing PV alone, doing solar alone, and so this gray part, this is, I've broken down the costs into categories. And then the little black dot here is the net profit. This is the net profit in $1 million. And this is for an 80-acre field. And so you can see they're breaking even with solar. They're making, on an 80-acre field, they are making about $90,000 in profits for the 80-acre field. And the biggest component of cost is CAPEX, the annual CAPEX, which is this part. And then when you compare that to integrated agrivoltaics, you can see here, the black dot is actually below 0. So it's a negative return. So this clearly shows the trade-offs between, this is land sharing, and you could think of this as pairing. So putting solar on by itself. So this is not going to be profitable for solar developers. And so the solar developers don't have any incentive to do this. We've had so many focus group meetings with developers. We've had meetings and workshops, and there is not a single developer that is going to be interested in taking a project like this. So this is what they're looking at. And then on the plot on this side, this is cost and return. So this is profits for the farmer. So this is from the farmer's perspective. Remember that in this setup, the farmer is making money, is earning income through leasing his land. And so the average cost, the average rate of lease is about $1,000 per acre. On an 80-acre farm, the farmer would be making $80,000 here, which is, this is the option here. So he's making $80,000 here. And then this red this portion is vegetation management. And so developers also pay farmers to take care of vegetation underneath the panels so that it doesn't grow too tall and impact on energy generation. And so farmers make another $365 per acre each time they do vegetation management. And so actually, from the point of view of farmers, they make a lot of money by leasing their land and by taking care of vegetation management. You can compare these with how much they would have made from corn soy production. So this is corn soy production, 80-acre field, and they would be making somewhere around 55 or 56,000. So they're making more money here leasing their land compared to this. And they actually make more money from an integrated system, because here the developer is paying less for the land. He's only paying for the portion of land that they are using for energy generation. So you can see they are already there's already a pattern here that's beginning to emerge. Developers cannot break even, are not making profit from agrivoltaics. They actually make profits only from PV. On the other hand, actually, farmers actually make a little bit more money by leasing their land to developers and getting paid for vegetation, and compared to doing just corn soybean. And so under agrivoltaics, we asked the question, how could it be profitable? How can policy ensure that agrivoltaics is profitable? Well, one way is by increasing electricity prices. So that is through increasing, so that is the feed-in tariff, the FIT. And so here we calculate a break-even electricity price that would make agrivoltaics as profitable as doing only solar. And so you can see this is under this part. This is the integrated agrivoltaics system here. Electricity prices would need to double from about $75.7 per megawatt hour, which is the average electricity price here in the US. Under agrivoltaics, you need much higher electricity prices in order to break even with solar. So that's one implication. You need higher electricity prices, maybe through feed-in tariffs, in order to support agrivoltaics. And then the other important question is the amount of land that is needed with AV to get equivalent crop output to that lost with an 80-acre utility scale PV field. So on an 80-acre field with only solar, you have no more crop production because you're doing solar. How about if you do agrivoltaics? And so we calculate on this first bar the amount of acres that you need to replace the production that would have been achieved on an 80-acre field, soybeans. And so you can see here, you need actually more land. So now you need 96.6. You need almost 100 acres of land compared to produce the same amount of soybeans as that you would realize on an 80-acre field. And so this starts to challenge the assumption that agrivoltaics is land saving, because you're using land for energy, for both energy and crop production. Actually, it's the other way around. Agrivoltaics is not necessarily land saving. In this case, you actually need more land to produce the same amount of food compared to doing crops only. And so I'm going to go to extrapolate. We're now going from a single farm. So that was all I've said before here was at a single site. This was single site. This was an 80-acre field. So we're going to go from an 80-acre field to the entire region. So this is the East Coast. We're going to extrapolate and look at how much land is needed to meet solar energy targets for the US for 2050. And so on this side, we calculate on the first plot that I'm highlighting here. This is the hectares of cropland that would be displaced under utility scale PV. So utility scale is going to displace cropland because the land is being replaced by solar only. And these are the hectares that would be displaced. This is at the county level. And so we meet we will be able to meet 82% of solar energy targets, which is, I think that's 1.2 terawatts. That's total target. And so we would, using solar only, we would be able to hit 82% of solar demand on the eastern coast here. And that's about 1.26 million hectares of cropland that must be converted. Again, so this looks like a big number, but in the context of the US land surface, this is about 1.67. So this is even less than 2% of cropland in the Midwest. Okay. The problem is, as I said, at the aggregate scale, it looks small, it's 2%. The impacts are not even, they're uneven. In 4% of counties, they need a lot of land is going to have to be converted. So they'll be losing a lot of land, much higher percentages in some counties compared to others. So like 10% of cropland would be displaced in about 4% of counties. And others would have almost zero. They would lose almost zero land because this selection here is based on the least cost way to do solar. So these are places that have the lowest cost of doing solar. And I will show that in the next slide. And then, so this is the percentage of cropland that would be displaced by utility scale. And you can see again, it's the distribution, and here's the scale. Okay. We have very, very small land use. This sort of light blue. And so the dark area is where there's moderate land use. So these are higher. So some areas have very, very high places where land would be impacted. And so it's very uneven. But on average, it's less than 2%. And then siting is driven by grid proximity, how close the land is to the transmission systems and the amount of land lease. So this is through utility scale. So this is the amount of cropland needed with alternative approaches, basically. So I would like to compare AgriVoltaics here with utility scale. So this is the same. Under utility scale arrangement, we would be hitting 82% of the projected demand targets. That's 1.26 terawatts. And then let's go to land sparing. If we do this land sparing approach, so let's put PV on low quality land. You may call it marginal land or land with low productivity. So this is land that comes in and out of crop production, depending on crop prices. So when corn prices are high, this land comes into production. When crop prices are low, they're not necessarily used. And so you can see here, we're only going to hit slightly less. So this is a bit less. So that's just 79% of projected demand. Not a big difference, but you're going to realize less. You won't be able to meet the targets on low quality land. And then under AgriVoltaics, it's even worse. You're only hitting 73% of projected demand. Okay. And so the histogram below here is the percentage of cropland displaced at the county level. And if you look at the sort of the purple bars here, this is utility scale on cropland. It has the lowest histograms, like the shortest, they're not as tall. And so they have the least impact. And then you can compare that with utility scale on marginal land, on low quality land. So that's the green one, and those are polar. So these are requiring more land. That's the percentage of land at the county level. So these are a bit polar. So you're displacing more cropland under this approach. And then under agrivoltaics, you also they're much taller compared to just utility scale. And so you're also displacing a lot more land. So these two are actually displacing more land. And so you need more land, and you're generating less energy. Those are the two things. Generate less energy with the land sparing and agrivoltaics, and you need more land, okay, on a sort of regional scale. Just to show this again, so this is the cost of energy. So this is the levelized cost of electricity and transmission, how much it costs to produce energy at the site, and the energy cannot be used where it's produced. It has to be transported. So it has to be put to the grid. And so the cost of transmission, so cables, interconnection, and there's often a waiting queue to get connected on the grid. So all those costs are factored in. And this just shows what I was saying earlier. So if you look at the utility scale, which is the blue bars here, you can see here they are the shortest compared to the green bars here, where you have more. So these are higher. So the cost of electricity with low quality cropland and on agrivoltaics are much higher compared to utility scale. And so again, these are the implications of doing agrivoltaics. When we started doing this research, we did not have this information. It's when we sat down and started doing the calculations that we started realizing that energy costs are going to be a lot higher with agrivoltaics compared to doing just solar alone. And so here I calculate the crop displacement. So using the information that I presented in the previous slides, we attempt to calculate how much quantity of corn, soybeans, and wheat will be displaced. So these are in million bushels of corn, of soybeans, and of wheat. And the thing I just want to highlight here is just the agrivoltaics. So agrivoltaics results in even greater crop losses for lower capacity and at a higher electricity cost compared to solar. And so you're going, as I said again, I keep coming back to this. You are producing, you're going to generate lower electricity and at a higher cost, and you're going to displace more crops. So agrivoltaics is more complicated than we initially thought. I'm not saying that it's not needed, but I guess the thing is it's where it's going to work best, which locations where agrivoltaics might work best. I can skip that. And so these are some discussion points. And today is going to be a much shorter presentation. This is not going to be long. So I do have some discussion points here, and then I will open up for questions. And so these are the main trade-offs with alternative approaches. And so using low productivity land, basically what it does, it spreads solar across 78% more counties. So it takes solar out, spreading it out. And then you get 4% less installed capacity. So less electricity capacity. Total land under solar is about 0.9 million hectares. And then the average cost of electricity, so it's going to be $80 per megawatt hour. That's going to be 9% higher than utility scale. So higher cost of electricity generation due to the distance from the least cost location, basically distance away from, the farther away the land is from the grid, the higher the cost of generating that electricity. Unfortunately, agrivoltaics only meet 79% of demand, and while raising electricity costs. So this results in the need for more land, so 2.56 million hectares to meet only 73% of solar demand. And you're producing 10% less energy, and you need 14% more land. And so this assumption that agrivoltaics is a land-saving technique may not add up, at least in terms of the economics. It doesn't stack up. 38% higher cost per megawatt due to lower panel density and that grid distance. And then AV adoption is more spatially dispersed, so it's going to spread out across the region. And so I dive here into the reasons for community opposing solar. So solar farming leads to an equal distribution of costs and benefits within the community. So there's this argument that landowners benefit more. So there's higher gains to landowners because they are earning the land lease. So those that earn the land actually get, they're the ones making that $1,000 per acre. In the process of doing this work, we've had so many workshops, so many focus group meetings with farmers. And I remember in Colorado, we met a farmer. He had 800 acres of land, and he's like, well, I'm more than happy to lease half of this. It's all full of rocks. I'm no longer farming it. And so the person that owns the land tends to benefit. And then the solar developers from low-cost locations. So solar developers are going to make profits because they're able to generate electricity on flat land, close to the grid, and so that's going to reduce their costs. And negative impacts, we will see negative impacts on tenant farmers. So the land, the rate for renting land for farming is, I think it's $100 per acre here in Champaign County. And so they are going to have to compete. They have to compete with solar developers who are paying $1,000 for that same piece of land. And so they already are at a disadvantage. So that puts them at a disadvantage. And obviously, when land is lost to agriculture, there's also loss of agricultural business and the supply chain impacts. And the biggest thing that we've come across in our focus group meetings with farmers is the loss of identity, this sense of identity and place. A lot of farmers want to continue farming, not necessarily for profitability. So profitability is one metric, but some people want to see and want to continue with that culture of farming, and they want to see farms still continuing and thriving. And so that has been one of the sources of community opposition. And then also there's an argument about transfer of income. So there's transfer of income from rural areas to urban areas, because most of that electricity is not consumed where it's produced. So it's going to be generated in the rural areas. It's going to be put on the grid and sent to Chicago. And so there is actually some kind of transfer of wealth from land in the rural areas to urban areas. And so the costs are being borne by rural communities. And so the benefits are kind of going to the urban areas. So we think these are sort of the biggest drivers of community opposition. And so the ultimate question here is then, can agrivoltaics enable solar farming? What are we getting? What is the purchase? What are we purchasing by doing agrivoltaics? So AV may provide what we call the social license to operate, because it allows some kind of farming activity to continue, which is appealing public sentiment. In the process of doing this work, we have encountered farmers, like a new breed of farmers that are interested in mowing. They're not interested in doing row crops. They're just interested in maintaining vegetation between the solar panels. That's actually, as I mentioned, that's $350 per acre. That's probably more than what you get from corn and soy production. And so you have farmers, probably tenant farmers, or they don't own the land, but they're interested in using that land, that unused space in between the solar panels. So that is one thing that AV would allow continuation. And so it's going to spread out solar farming over a larger land area. and so allows tenants and small farmers to access the land because some kind of farming is continuing. It also makes solar developers look good. It's good for their image and reputation. So that's the only reason solar developers, at least in the US, are interested in doing, because it makes them look good. It shows that they are promoting ecosystem services by planting vegetation underneath the solar panels. They're helping to keep some of the land in agriculture. But other less appealing features is the need to change crops. So changing crops that can be grown. You can do soybeans. The figure I showed was a stylized design configuration using soybeans. But imagine if you had corn, because corn is going to grow even taller. And so it would be even more difficult with corn, because then you need maybe 10 feet. You need panels that maybe 4 meters above the ground. And that would be costly. What we know is that every feet that you go above the ground, you need to go underground twice, 2 feet underground, because of the structural, to make it structurally feasible and strong. You have wind loads in the Midwest, you have very strong wind loads. And so you need to secure the foundation. And so that just increases, again, the engineering costs. And it may require changing equipment. As you know, this part of we have very big combines here in Illinois. So imagine a big combine, coming through in between solar panels. So we've been talking to farmers about possibly using small equipment, all of which means higher costs. And then it's going to increase the cost of electricity in the region. And so in summary, AgriVoltaics, basically, based on our research, it actually expands the footprint for solar energy deployment. It increases. It does not save land. It actually increases the amount of land that is needed for solar. You need even more land. And so this could actually even drive up community opposition in some places. Will require expanding cropland to maintain crop production levels. So you need more land to realize the same crop productivity. It may help reduce opposition, but it doesn't guarantee equitable outcomes or lower costs. It creates both winners and losers. And so new business models are required. You need policy incentives. You've been following the news. Solar incentives are going to expire. So this is going to be even more challenging. And then we need site-specific designs which are optimized for scaling up EV. Energy transition debates must account for these local trade-offs. This is where the community opposition is coming from. People, the citizens that are not benefiting, the tenant farmers, the neighbors that are not getting anything from solar that is deployed in their community. And you need strong community input. So basically, these are the main things I was hoping, and I think I've tried to keep this short. So thank you so much. This is all I have today. I'm very sorry, there's a little bit of background noise here. I hope that has not distracted you. Thank you so much, and I'll be happy to take any questions.
Okay, thank you for that, Paul. Yeah, really interesting. Yeah, interesting piece of work. It wasn't what I was expecting, to be honest. I was thinking you were going to come and tell us it was all good work, really. So I was quite surprised. But yeah, it's certainly an interesting piece of work. There aren't any questions in the chat, so I'm happy to open up the floor if people want to ask any questions of Paul while he's on. I think one of the biggest challenge, certainly like in the US, you've obviously got an abundance of land.
Yes.
I think you take somewhere like the UK, I think there's a lot of sort of negativity around agricultural land going to solar. And you read a lot in the press about it, but ultimately it's the landowners that are making the decision, so people will moan and groan about giving up farmland for solar, but unfortunately it's the landowner's decision. Nobody's forcing the landowners to do it. And some of the money on offer is incredible. With 40-year leases that are index linked and paying
Yes,
substantial amounts of money. It's hard
absolutely.
as a landowner to just turn away from that, So,
Absolutely.
but equally,
And
there's the moral obligation there that we need the land to produce food.
yes, yes.
Charlie,
And just
Charlie, can
uh-huh.
I just
Yeah.
come in here?
Oh, Mike, sorry, yeah, go for it.
I'm actually directly impacted by some of the mega solar developments. I don't call them solar farms because they're not farming. Sorry, I'm a bit obviously coming from a being directly impacted by the Highgrove development, which has been in the news around between Dereham and RAF Marham in the middle of Norfolk. And we've also got, which is about 4,000 acres, but in my parish of Spall, which is just northeast of Swaffham, we will have at least 1,000 acres. We have at least 1,000 acres planned for a mega solar development.
Yeah.
Now we're very close to Necton, where the two large offshore North Sea wind farms, where their electricity comes into the grid. It's two large, there's one already constructed, one being constructed at the moment, large national grid substation, which took years for them to get through because of opposition. But we're very close to the grid. And what has really intrigued me is what Paul's saying is the whole business around the opposition and how people feel about this. I mean, I was coming today hoping there might be some interest or light in the tunnel with, like you, I was a bit, oh right, okay. But I can see exactly where Paul's coming from in terms of what his research, and it makes eminent sense. I think probably the thing is it would seem to me that you've got to look at agrivoltaics on individual geographical sites with particular soil conditions, with particular cropping needs or possibility of cropping needs, and it needs to be done on a much smaller scale. I mean, yes, round here, yes, wheat, barley, sugar beet, potatoes, onions, that sort of thing. But it's the problem is that there is this inequity within what's going on. And it is a thing between rural and urban because all the electricity that's being generated is going down south. And there's a huge row going on about the Norwich to Tilbury pylons or a new grid line. But the whole problem, it seems to me, I don't know about America, but the whole problem with the whole of this business with renewables is we've suddenly jumped into renewals over a very short period, and nobody anywhere has thought about the transmission of power. The problem, it seems to me, is my background before I retired was building grain stores and potato stores and that sort of thing in East Anglia. And the problem we found is there just wasn't the capacity to actually even put large roof mounted solar panels on large grain stores. And because the distribution guys would say, well, we haven't got the capacity to take it. And we just haven't thought about this in any great detail. And now we're in a situation where we've got, in Norfolk, it's something like, I think there's something like 40,000 acres.
Really?
Has got sort of planning on it. But it really, that there is one thing I would say, and I think it's probably, you might want to comment on some of the other questions. Is some of what you've said today seems largely irrelevant to a UK situation, because we have higher population density and we have far worse food self-sufficiency. And I don't know how you'd want to address that, Paul. So sorry, I've made a big comment.
No, that's okay.
or a blast, as it were.
That's
But that's my question at the end of it, Paul.
that's okay. I absolutely agree with what you're saying. There's also comments in the chat. And just to clarify, I wish I had better news on the especially on the profitability and the economics.
Mm-hmm.
What's driving these negative results? We tried to look for where it might work, but with raw crops, with pole crops, with soybeans, it's a challenge. But if I presented these results with like specialty crops, tomatoes, vegetables, spinach, strawberry, we would be looking at very, very different results. Yeah, and places like California, Arizona, that they would actually, where they have water shortages, AgriVoltaics would actually help save them water. So it might actually work really well for other crops, specialty crops, vegetables, some fruits, grapes. It's going to work much, much better. They are shorter. They don't require lifting the panel up. They don't require all this spacing. And so it's going to be much, it's going to look much, the economics will be upside down if we go to Arizona and California and all of that. So that's the problem here is with raw crops. The fact that raw crops, we're dealing with raw crops, they need a lot of sunlight. They compete with the panels for sunlight. So corn requires so much sunlight. That's the thing. And corn is very, very tall. So that is basically in terms of crop choice. And you're right, the comments again here, I saw in the chat about small scale systems. I think that's probably better. That's going to work better. Small scale systems, maybe with tomatoes and things like that, it's going to be really, really perfect. This argument of producing all the electricity in Arizona, the problem is Arizona is a desert. No one lives there. So again, you need to move that electricity from Arizona to send it to the big population centers. So there's again a cost of generation, cost of transporting electricity. So that's going to be a challenge. But I think maybe what I would say is agrivoltaics is going to work best with short crops. It's going to work best with specialty crops, small scale, community scale farm, that kind of thing is going to work best. I missed the last question that you asked. You mentioned, you talked about population density, and was it the battery thing you mentioned?
I mentioned about the fact that the UK is a high population density,
okay.
High population density, and we have lower food self-sufficiency. So
okay.
the questions
Yes.
about, whether we should use more land for solar and or cropping becomes a much more, you said that a lot of people in the US or in your part of the US that you're looking at oppose it on the basis that it's taking land out of food production, which is the biggest response that we get from people here.
Yeah. So that is that's the big problem here too. I went to 2 months ago. I was at the Champaign County public hearing. So whenever a solar project is proposed, it has to go through the county hearings. It's a public hearing. If you are pro or against, you stand up, mention your name, and explain why you're opposing this project, why you're supporting it. And that's the biggest thing. Is food production. Land being taken away from food production. So that's in common. That's the same problem. Huge amounts of land. So it remains a challenge. Yeah.
Okay. So what? If we can we move on to David Clare, who's patiently had his hand up, and then we can have a look at some of the questions in the chat.
Yeah, I was just going to say, has anybody done any studies looking at integrating with animals?
Yes. So that's, I can answer that straight away. That's basically a marriage in heaven. So that's the best combination for, you can't go wrong. So we get that question when we were doing this research. That's what farmers told us. What about sheep? You know,
Mm.
solar panels and sheep is the best combination. Sheep is gentle. They help to maintain the vegetation. So they eat the grass under the panels. In the afternoon, the sheep actually benefits from the shading, like to avoid the intense heat. And so the sheep actually, they stay underneath the solar panels and enjoy the sort of cool space underneath the panels. And so that really works well. There's a very, very strong community here doing solar grazing. We call it solar grazing. It works really well. It's profitable. It helps both developers and helps farmers. There's research going on looking at other animals. So like we've been told you can't do goats because they're very aggressive and tend to attack the solar panels, like jump on it. Cows a little bit, if they lean on the panels, that causes structural damage. So that's probably still, but there are examples of like taller panels with cows, although they're on the heavier side, could potentially damage the panels. But the best combination that I've seen, and that is, there's actually a movie on that, is solar panels and sheep. Best combination.
I've done some work on this in the past, and the other type of farming you can do is to do with poultry. So you can actually
Yes.
put geese in particular, as long as you've got electric fence around the outside to keep the foxes out.
Yes.
But yeah, you can do some free range stuff. But sheep, I think, are definitely the best. I don't know whether that works in California or not.
Well, that's a really great example. In Australia, they do poultry. They also do rabbits.
Yeah.
So rabbits underneath solar panels is a great combination. So those are the kind of areas that might be more feasible. We do have this. We still have that problem that you have millions of acres of land that are under corn and soy production. And so basically what you're doing is, what our results is saying that is that those farmers, corn and soy farmers, will not be part of agrivoltaic.
Mm.
That's the downside. There's millions and millions of acres that is.
I think in the US as well, there's a lot of energy crops grown as well, isn't there? People growing
Yes.
corn for ethanol production as well. Do you want to have a look at some of
Yes.
the questions in the chat? So just, I think some of them are more comments, but Nigel Penlington, can you see the chat, Paul, or do you want me to read the question out? Or...
Let's see.
Nigel can unmute if you want and ask a question. That's usually how we do it.
Have farming practices been adopted along regenerative farming lines to allow for beneficial insects such as pollinators to increase in the margins, which will then allow a reduction in pesticides, improve soil health, to reduce costs, but also increase, there's more and more evidence showing that where pollinators, for example, are present, you're getting increased yields?
Yes.
Or is it just purely done on conventional ag chem farming methods?
No, that's a great question. The majority of PV sites are actually doing pollinators. So that's a fantastic question. And I think there's a study from Argonne Laboratory that was measuring diversity of pollinators around the solar sites across the US. And the results are really, really fascinating. There's huge increase in abundance of insects that are then helping nearby fields. I would say 90% of solar sites are doing pollinator habitats. So along the line of regenerative agricultural principles, they're doing exactly that. So that's one of the positive news on agrivoltaics with pollinators. Some people argue that that's not, it doesn't lead to food production. There's a word for it, it's called ecovoltaics. So producing ecosystem services, basically increasing population of pollinators around the solar panels. And American Farmland Trust has a definition of what constitutes agricultural production, and they do not consider ecovoltaics as agricultural production. It doesn't necessarily lead to food production, but it's a very, very big thing. It's a big deal. They're doing it at almost all the sites. I know people that go to the solar sites to take measurements almost on a weekly basis, and the results are really, really good. As with these things, some people are also installing beehives around the solar panels. And it's just difficult. It's a slippery line between greenwashing, because that's what the term they're using, because it doesn't lead to like direct food production. There have been some headlines about, pollinators and bees, pollinators, and is a form of greenwashing. But yeah, there's a huge increase in that.
Okay. So we've got time for one more question. Do you want to, Sarah Parsons, do you want to unmute and ask your question? And then we'll call things to a close.
Thank you. Good afternoon. I'm aware that the increasing number of sort of great big data centres has been problematic because they are concentrated in certain areas. And looking on one of your slides, there's a very noticeable concentration of the, what did you describe it as? One of your metrics. Anyway, big concentration up in the northeast. And I wondered if you could explain what that northeast concentration is mainly based on, and also how the sort of increase in data centres is impacting really the whole US grid. I was interested to know your informed sort of insights into that, please.
Yeah, that is a fantastic question. We're actually looking at demand from data centres. I saw in the news last week, Google, or one of them, has bought the huge amount of land, almost the size of Staten Island, and they're actually going to build their own solar panels so they can produce their own, they can meet their own energy needs. So there is a huge demand in electricity from data centers. There is probably the largest is in Virginia, a very big data center that is consuming so much electricity. And so solar panels are actually the perfect locations and the perfect places for that kind of thing. The maps I showed are actually based on the lowest cost to do solar. So we calculate the what we call the levelized cost of solar, basically the average cost of producing a megawatt hour of electricity. And then we say, where is it cheapest to do it? Which areas, which it's like a 4x4 kilometer grid. And then we point to areas where it's cheapest to do it. So that's where the concentrations are in the northeast there. That just shows where it's cheapest to produce solar. It may be the case that data centers will go there, but that's what we're looking at next. We're trying to link this increased demand for energy from data centers and how that is linking to solar farms that are being built. But that's a fantastic question. We might could be like one of the things we do next to link. I don't know what we call it, linking agrivoltaics or linking solar farms to data centers. We're trying to make that link.
Okay, well, we're just about on the hour, so I'll draw things to a close. So thank you, Paul. It's a subject that continues to get a lot of debate. And I'm sure it will continue to do so. So thanks for taking your time out to do that. It's very much appreciated. Thank you to everybody for joining us today. I hope you'll join us for our next lecture on the 14th of October, where we'll be joined by Adrian Hill, who is the technology manager for Morris Lubricants. While everybody's on, I'd also like to remind people that booking is now open for our annual conference, and that's on the 22nd of October. And this year, the conference is going to be online, and we're going to be looking at artificial intelligence in agriculture. We've got some great speakers lined up from industry, including AGCO and CLASS, plus some leading academics as well. So please get yourself registered. So all I have to say is thanks again, and we'll see you next time. Bye-bye.